everyone, I am Sanya Kole. This is cute little Tugger. And this is cute little Yankee. And in this video, we'll be talking about how you can interpret various probability thresholds in decision curve analysis. For instance, the probability threshold of 10%, 25%, the default 50%, 60%, 80%, and other probability thresholds in any application like coronary heart disease. I have another detailed video where I'm talking about specifically interpreting 25% as a probability threshold. But here, Yankee, we have back to back examples and quick walkthroughs of just what these probability thresholds mean in terms of false negatives and false positives, and in terms of clinical net benefit interpretations of false negatives and false positives as given by decision curve analysis. So if you've ever struggled to understand what these probability thresholds mean, like back to back, then this is the video for you. And if you want more detailed behind the scenes of each step, from machine learning models to confusion matrices and what all of those mean, then please do see my other video that's detailed walkthrough for a probability threshold of 25%. Because in this video, I'll just be going through a bunch of different examples for those of you who already kind of understand a little bit about false negatives, false positives, and just want to see different interpretations of probability thresholds. So the link for my decision curve analysis playlist is in the bio. So please do subscribe and check out those other videos. But again, I'll be just talking through, for instance, if we have a logistic regression machine learning model or any machine learning model for any condition, not just heart disease. You can see these cute little hearts. These cute little hearts, Yankee. But you can see that this application could be anything. And when we have probability thresholds and we are varying them, what does this mean back to back? And how does that change, right? Like if, based on a probability threshold, anything above that probability threshold is assigned to a positive class. Anything below is assigned to a negative class here. So here patients are predicted as negative and if below a probability threshold of 25%, and here they're predicted as being positive. And here we'll be walking through a lot of different examples for all these various probability thresholds. So let's get started, little guy. Who wins the tug of war when we're looking on two sides for a probability threshold? Either we can go for treatment and these little ones are pulling in that direction, and if we're going for treatment, they win if the predicted probability of being positive, of being in the class that needs treatment, is greater than or equal to some probability threshold PP. So if the probability that an individual or a patient here is positive is greater than or equal to a threshold, then you're predicted as being positive, and then you need to go for treatment. Otherwise, you're being predicted as negative, and then these guys win if the predicted probability for a patient being positive is less than the threshold. They're predicted as being negative, and then the idea is not to go for treatment. So it's just like a tug of war. Who wins? On this side, they're saying, go for treatment. And on this side, they're saying, please don't go for treatment. They say, don't go for treatment. And they're saying, go for treatment. So you go for treatment if the probability of being positive is greater than or equal to a threshold. Otherwise, you don't go for treatment. And it's all based on your probability threshold. And indeed, Yangshi and I are going to see what happens as we change this probability threshold, from 0 to 1. And who will win this tug of war? We're going to be changing the probability thresholds and seeing who ends up winning this tug of war, Yangshi. Who ends up winning this? And we're going to see between 0 and 1 as we change this, who's going to end up winning? Who's going to end up going for treatment for any given disease or condition, or even if it's not disease or condition, anything. Oh, it's a little tug of war with you. A little cocky, different little guy. You want to play a tug of war game with me? thresholds are just like a tug-of-war. You see him pulling and me pulling? It's all like a tug-of-war. Just like a tug-of-war. Oh, he lost. So in decision curve analysis, we typically select a probability threshold and a positive test for a patient or an individual is if the predicted probability of being positive is greater than or equal to that probability threshold we select. Otherwise, they are predicted negative. And then we calculate the clinical net benefit as the true positive count divided by n, the number of individuals in our training data set, minus the false positive count over n. And then we multiply the false positive count by the probability threshold divided by 1 minus the probability threshold. And then we vary the probability threshold, across 0 to 1. And I have other videos going through decision curve analysis and another one that's going through the probability threshold of 25% in a lot of detail. So please do subscribe to my channel. Please do watch those videos for more explanations on DCA and this formula. But a key thing I want to show you is that this ratio, this fraction of PT over 1 minus PT, the probability threshold over 1 minus the probability threshold, is actually equivalent to the false positives over the false negatives, where false positives are falsely predicting a healthy patient does not have the disease. Predicting that the patient is healthy, that they don't have the disease, but they actually have the disease. So that's a false positive. But so when a false positive, you're predicting again that a healthy patient has the disease, and in a false negative, you're falsely predicting that a patient who actually has the disease does not have the disease. So this is the ratio of false positives, falsely saying somebody who's healthy has the disease and is positive, so they're sent for unnecessary treatment, the false positive, divided by the false negative, saying that the patient who actually has the disease does not have the disease, so they are missing out on the treatment that they would have needed. So that's what this ratio tells us, essentially. So please recall that we talked about in an earlier video, and I go into this in more depth, about how you can look at these probability thresholds, threshold probabilities, PTs, and how you can interpret the consequences of a false negative versus a false positive. And as a recall, a false negative, as Yankee saying, just a recall overall, a false negative is when you falsely predict that someone who is actually positive, who has a disease or condition, that they do not have it. That's a false negative. And a false positive is when you falsely predict positive. So when you falsely predict that an individual has a disease when instead they're healthy. So based on these thresholds, and I go over this a lot more in a whole other video, so please do see that, Yankee saying. So when the threshold probability is 50%, then false negative and false positive mistakes have the same impact. Both are equally bad. And the idea is that based on these probability thresholds, we can see how we weight these different types of mistakes. Like if we had to make a mistake, what would we prefer making? So here, false negatives and false positives are equally bad. But in the case where the probability threshold is less than 50%, in that case, a false negative is a worse mistake than a false positive. So we rather make more false positive mistakes than false negatives. And on the other hand, when the probability threshold is instead greater than 50%, so it's kind of opposite from this, the false positive is instead a worse mistake than a false negative. So these two are kind of like opposites here. And this 50% is more like the default. It's like the default in general. So let's get started because, I have a whole other video. So please do subscribe and see that video as well. And I have a video talking all about this and this intuition. But please do reach out if you have any questions. And I have another video where I'm just talking about what 25% means as a probability threshold, a very detailed video. But here we talk about many probabilities. We will talk about like 5% as a probability threshold, about 25%, which I talked about in another video, but then we talk about it again here. We talk about 40% as well. What do these probability thresholds mean in terms of false negative and false positive mistakes? 5%, 25%, 40%. And then I kind of talk about 20% as well. I don't go into too much depth about 20%, but the reason I include this is because I sort of want to compare this 20% probability threshold with the opposite of 80%. So basically, what I end up doing is I end up kind of comparing, this 20% here with this 80% in this example, and I show how they kind of are the opposite idea of each other. Because 20% and 80% add up to 100, so the interpretation of false negatives and false positives for 20% as a threshold probability will be the exact opposite as the interpretation for 80%. And that's the case for like 75% and 25%. The interpretation will just be like flipped around. It will just be the opposite. And similarly for like 40% here and 60%. And for 95% and 5% here, the interpretation will just be opposite because these sum up to 100%. These 40% and 60% sum up to 100%. 25% and 75% sum up to 100%. 20% and 80% sum up to 100%, and so on. And there's so many more examples that Yankee's saying. There's so many more examples that we really really hope that these will help you understand this whole, field and understand how to interpret a probability threshold. That's what we're hoping. So I'm giving you these few examples here, but we can analyze so many, and I'm trying to give you a framework. Like for 90%, the opposite interpretation would have been for 10%, so you will notice that. But I'm trying to give you just a few different examples, and I hope that those will help you. And again, like, please reach out, but this is the kind of where we're going. We'll be seeing that this interpretation for 5% as our threshold will be the exact opposite as for 95%. And for 20% will be the opposite for 80%. So basically, if we have any threshold here, the opposite, here, if as long as it adds up to 100%. So if, for instance, we chose like 15% here, then the opposite would hold for like 85%. And we'll be going through that, so 15% and 85%. So we'll be talking about these main probabilities, and then I'll be showing you the intuition. Basically, how is a probability threshold like a currency? How can it kind of just tell us the way that we weight, the false negatives and the false positive mistakes? How? So let's get started and check this out. So Yankee's all revved up. So he's saying to please watch our other videos if you are confused, and please do subscribe. Yankee's saying to subscribe below. So next, Tuggle and I will look at situations when false negatives are worse mistakes, and that's typically when a probability threshold is less than 50%, Tuggle. So a probability threshold of 5%. So what this means is that the clinician chooses to treat a patient, using this threshold of 5%, essentially predicting negative if the patient's predicted probability of disease is less than 5%, and then predicting positive, that the patient has disease if instead the patient's predicted probability is greater than or equal to 5%. So this is the cutoff, 5% here. So below 5% predicted probability, please predict negative. Otherwise, please predict positive for the patient using this threshold. So what this threshold of 5% means, so we can put in for probability threshold divided by 1 minus probability threshold, we put in 5% for the threshold divided by 1 minus 5%, and then we set this equal to false positives over false negatives using the idea from decision curve analysis. So this is what the formula becomes here. So then we simplify this here. So this is 5% over 95% equals false positives over false negatives. And this simplifies here to 1 over 19. And then we again set it equal to false positives over false negatives. So then we multiply these two together and then these two together, like cross multiplication. So that means that 19 false positives are equal to 1 false negative. So what this means here is that for the clinician, making one false negative mistake, not treating a diseased patient, that is 19 times worse than the consequences of a false positive when you're treating a healthy patient. So this shows that the clinician really wants models with as few false negative errors as possible, because one false negative is the same as making 19 false positives. That means that ending up with one false negative patient is the same or worse than ending up with 19 false positive patients, because one false negative is 19 false positives. So here you really want to predict positive as much as possible, because having a false negative falling in this interval is 19 times worse than this being the case. So when you're predicting positive here, you could either land up with a true positive or a false positive. And when you're predicting based on this threshold here, you could either land up with a false positive or a false negative. So by having this threshold of 5% here, then you're really trying to limit the false negative, the chances of a false negative, as much as possible, even though the chances of a false positive go up here from this prediction of positive. So that's what this probability threshold of 5% means here. False negative 1 is 19 times worse than the consequences of a false positive. Actually, I want to kind of apologize. I made a small little mistake on the previous slide. So when we are predicting positive for a patient, then either we are correctly predicting the patient's positive, so it's a true positive, or it's incorrectly being predicted. The patient's incorrectly being predicted positive as having the disease when the patient does not, so false positive. So when we're predicting positive, either it's a correct prediction, a true positive, or it's an incorrect prediction, which is a false positive. On the other hand, if we're predicting negative, which is what we do if the patient's predicted probability of the disease is less than 5% in this situation, we are predicting negative, that the patient does not have the disease. And in this case, either we are correctly predicting, so this should be a true negative. So sorry, this should have been a true negative. Either we are truly correct when we say that the patient does not have the disease, a true negative, or we have made a mistake and the patient actually had the disease and should have been considered positive. So whenever we're predicting negative for the patient, either we're correct and it's a true negative, patient truly negative, or it is a mistake and we have a false negative. So whenever we're predicting negative, if we're correct, it's a true negative for the patient. Otherwise, if it's incorrect, it's a false negative for the patient. Whereas if we're predicting positive based on this criteria, then whenever we're correct, it's a true positive result. Otherwise, whenever we're incorrect, it's a false positive result. I just wanted to clear up that this should have been a true negative instead of what I just showed you. So here's an example of an application of a probability threshold. So let's say that a clinician chooses to treat a patient who has a predicted probability of CHD, coronary heart disease, that is 25% or above. That is that the clinician has a probability threshold of 0.25. So on the scale here of probability thresholds between 0% and 100%, this is the clinician's probability threshold, 25%. So this is where the clinician is at. And that's where the clinician's threshold is at 25%. So then based on this weighting, so probability threshold over 1 minus probability threshold, so PT over 1 minus PT, then what we're going to see is that, it's 0.25 over 1 minus 0.25. From the equation I showed you, this is just the same as false positives over false negatives. That's how you can interpret it. So basically, the patient will be treated as long as he, she, they has a predicted probability of CHD that is 25% or above. So if you have at least a 25% chance of having coronary heart disease, then the clinician automatically assigns you to the positive class and predicts that you will have CHD and then decides to treat you. So then based on this, all you do is this is 0.25, this is 0.75, which is just the same as 1 over 3. 1 over 3 equals false positives over false negatives. So then from this equation here, you just multiply this side by 3. 3 times false positives equals 1 times false negative. So 3 false positives is equal to 1 false negative. So that's how you can kind of interpret it. For every 3 false positives that you make, it's the same as 1 false negative. So in the mind of the clinician believes that the consequences of a false negative, not treating a CHD patient, are 3 times worse than those from a false positive, so treating a healthy patient by thinking they have CHD. So this shows that the clinician really wants models with as few false negative errors as possible. Because if you think about it, with this being really low, already the typical prediction model usually assigns positive if you're above 50% and negative if you're below 50% as the threshold. So if you already are assigning, so basically based on this threshold, you're assigning everyone here as being positive. Anybody who has a predicted probability of 25% and up, you are assigning them to being positive. And then the rest you're just assigning to being negative below. And so basically, it's so much more common for you to assign people to the positive class where they will get treated for CHD. And because of that, what happens is that you are not weighting them equally. If they were 50% and 50%, like if the threshold is 50%, like it is for many prediction models, then what that means is that false negatives are the same as false positives. But here, and that's what typically prediction models do, they just assign 50% and up to positive, 50%, below 50% to negative, because false negatives and false positives typically are assumed to be equal. But the benefit again from decision curve analysis is that that may not always be the case. So you want to be able to just adjust your model based on your threshold, because you may not want to assign everyone to positive if it's 50% and above. You might want to have like 25% or 10% or maybe 80%, But because this is below 50%, you can kind of have a sense that false negatives are worse than false positives. So you really don't care if you're assigning them to the positive class that much, because since it's a greater chance of you assigning them to the positive class, there's a greater chance of false positives, and that's what you're willing to take. Here's like the false negative risk, but you're so willing to take that risk of having the false positives be higher because you're too scared of a false negative. You're too scared that somebody with a 25% chance of the CHD could still potentially, in your mind, be at a really high risk of CHD, and if we don't treat them, it can be worse, right? So that's where you are, that if they have such a high probability, like 25% might be high to the clinician or to the loved ones of the patient. So they might want to just get them treated. So that's how you interpret it. So usually if your threshold is below 50%, then a false positive is not as bad as a false negative. So in terms of errors. But here, like false positive is not as bad as a false negative. But if the threshold is above 50%, then in your book, the false negative is not as bad as a false positive. So when we said that the probability threshold of 25% essentially says that 1 false negative equals 3 false positives. So again, not all errors are created equal. when the threshold probability is 50%, then a false negative. One false negative equals one false positive. But here at the probability threshold of 25%, one false negative in the mind of the clinician is equal to three false positives. That is the utility to the clinician. So having one false negative is the same as three false positives, or probably even worse than having three false positives. So wrongly predicting that one unhealthy patient who truly has coronary heart disease is healthy, the mistake of making a false negative, of wrongly predicting that SpongeBob is healthy, that results in SpongeBob missing out on necessary treatment for coronary heart disease. This mistake is probably equal, if not worse, than the mistake of three false positives, of wrongly predicting that three different patients, three different healthy patients with healthy hearts, that they have coronary heart disease and sending them for unnecessary treatment. See here, the doctor is telling all of them, I'm afraid this doesn't look good. And all three of these patients are saying, please don't tell me I have CHD. Please don't tell me I have CHD. Please don't tell me I have CHD. They actually have healthy hearts, and now they'll be sent for unnecessary treatment. And at this probability threshold of 25%, the doctor is so scared of having a false negative. Essentially, in his, her, or their mind, this mistake here is equal, if not worse, than these three mistakes. The fact that this unhealthy heart is missing out on vital treatment is worse than three healthy patients going for CHD treatment. So you might agree with this, or you might disagree, and that's why this is subjective and why we have these probability thresholds in the first place. But this is how you can think about it. So if the probability threshold is raised to 40%, so again, it's still less than the 50% mark here, but if it's 40%, so instead in the formula here for probability threshold over 1 minus probability threshold, we put in this 40% here. And again, what the prediction is negative, which means that the patient does not have the disease if the patient's predicted probability of the disease is less than 40%. Otherwise, we predict that the patient has the disease, that the patient is positive, if this predicted probability is greater than or equal to 40%, based on this threshold. So less than 40%, please predict negative. Greater than or equal to 40%, please predict positive. So plugging into this formula, we have 40% over 1 minus 40%. We set it equal to false positives over false negatives. This is just 40% over 60% equals false positives over false negatives. So 2 over 3, this simplifies to 2/3, equals Fp over Fn, and then we cross multiply again, so we get that 3 false positives is equal to 2 false negatives. So if we divide both sides by 2 here, we get that 1.5 false positives equals 1 false negative. So what this means is that the clinician believes, so what we want to do is we always want to set it equal to the unit of 1 on one side. So 1.5 false positives equals 1 false negative. That's what we want to do. So the clinician believes that the consequences of a false negative, not treating a diseased patient, that those are 1.5 times worse than the consequences of a false positive, treating a healthy patient. So basically, not treating a diseased patient, predicting they don't have the disease when they actually do, and so not treating them, that is 1.5 times worse than unnecessarily treating someone who doesn't have the disease. So the clinician really wants models with as few false negative errors as possible. So again, in other terms, ending up with 2 false negative patients, it is the same, or it's worse than ending up with 3 false positive patients, because, again, 1 false negative is equal to 1.5 false positives. That's what this means here. And I have shown this visually here, is we have this cute little example with Patrick hugging SpongeBob, best friends here. So let's again just visualize, what coronary heart disease means here at the threshold probability of 40%. So this could be any disease, but here, for coronary heart disease, we're just going to focus, for example, on this situation here. So again, we just found out that for the probability threshold of 40%, essentially 2 false negatives is equal to 3 false positives. So in a way, what we can observe here is that we want to make as few false negative errors as possible, because 2 of these false negatives, so in this situation, wrongly predicting that 2 unhealthy patients, like, SpongeBob and Patrick, they're actually unhealthy, but here we are predicting that they don't have the disease, that they're healthy. We're predicting they're healthy, so here they're celebrating, but in reality, they actually have the disease. Their hearts are very unhealthy. Help! The heart is very, very unhealthy, Yangshi, but instead we wrongly predicted that they were healthy, and they're wrongly celebrating. So they miss out on necessary treatment for heart disease. So making this mistake for both of these patients here, wrongly predicting that they're healthy when they're not, is the same, or even worse than 3 false positives. And in the false positive situation, we are wrongly predicting that 3 patients who actually have healthy hearts, we are wrongly predicting that they have heart disease. I know that's a very sad disease, Yangshi. We're saying that wrongly predicting that 2 unhealthy patients who truly have coronary heart disease are healthy, and having both of them miss out on necessary treatment, the consequences are the same or worse than the consequences of wrongly predicting that 3 healthy heart patients actually have coronary heart disease. So wrongly predicting they have CHD when they do not, and they get unnecessary treatment. So this unnecessary treatment for them, for 3 patients, versus missing out on treatment for 2 unhealthy patients. So that's sort of what this means here in terms of the consequences. Wow. And that's why we want to minimize false negatives as much as possible. 2 false negative patients, 3 false positive patients. Next, we will talk about when false negatives are equal to false positives. And that is a default. Like, a probability threshold of 50%, then both mistakes are equal. So for this probability threshold of 50%, like a coin flip, the clinician chooses to treat a patient if the patient has a predicted probability of the disease that is greater than or equal to 50%. So that's a default. Usually if you are above, greater than, or equal to this threshold of 50% here, then we predict, positive in this direction. If you're less than the 50%, we predict that you're negative. But if you're greater than or equal to 50%, we predict you're positive. Plug in into this formula 50% here over 1 minus 50%, and then set that equal to false positives over false negatives. So when we simplify this, this is just 0.5 over 0.5, and then that is equal to false positives over false negatives. So this just slashes and thrashes out to just being 1. So then we just have like 1 equals false positives over false negatives. So here 1 false positive is 1 false negative. So they're equal, Yangshi. So thus the clinician believes that the consequences of a false negative of not treating a diseased patient are the same as the consequences of a false positive treating a healthy patient, believing that they have the disease. So that's kind of like the default. Now when we look at these 50% probability threshold, it's like a coin flip, flipping a coin. And again, for coronary heart disease, what this essentially means in this situation is that both errors are created equal. 1 false negative is the same as 1 false positive. So wrongly predicting that 1 unhealthy patient who truly has CHD is healthy, and giving this unhealthy patient the idea that they don't have it, that they're healthy, so they're missing out on necessary treatment. That kind of consequence in this situation is the same as 1 false positive, as wrongly predicting that a healthy patient with a healthy heart has CHD and giving them unnecessary treatment. So that's what this means when both errors are created equal. When 1 false negative equals 1 false positive, we have no preference. We just want to minimize both errors. And in any case, we do want to minimize false positive and false negatives. It's just like which type of error is worst to us. That's what we're trying to determine from these probability thresholds. And lastly, we will talk about when false positives are worse mistakes than false negatives, and that's when the probability threshold is greater than 50%. when the probability threshold is greater than 50%, then false positives are worse mistakes than false negatives. So the clinician is going to always want to minimize the false positives, even by having more false negatives, by assigning more people to the negative class, even if that raises the false negatives, because false positives are worse mistakes to the clinicians or to the people here. And for a probability threshold of 60%, well, we're seeing that instead we're more than 50%. So in this situation, if our probability threshold is greater than 50%, then it means that false positives are worse mistakes than false negatives. That's what we're trying to do. We really don't want to be predicting positive as much as possible, like if it's wrong. So what this means is that essentially we are predicting for patients negative that they don't have the disease if their predicted probability is less than 60%. So we're predicting that patient is negative, that they don't have the disease. Otherwise, if the patient's predicted probability of disease is greater than or equal to 60% our threshold, then we predict positive. So when we predict positive, guys, again, we can land up with these mistakes here. We could land up with either true positive or false positive. But if we end up with predicting negative, it can either be a true negative or a false negative. And in this situation, there's a greater range when we're predicting negative. So greater chances of a false negative relative to a false positive. See, this is just a positive section, much smaller than the negative section. So here we don't mind making false negative mistakes as much as false positive. So it switches around. And the way we can see and quantify this is by plugging into the formula the 60% as our threshold. So for probability threshold over 1 minus probability threshold, instead we plug in 60% and then 1 minus 60%. And then again, set this equal to false positives over false negatives. And then this is just 60% over 40%, which simplifies to 3 over 2 equals false positives over false negatives. And then we cross multiply this part and this part here. So 2 false positives equals 3 false negatives here. And then we divide both sides by 2. So 1 false positive is equal to 1.5 false negatives. So the clinician, based on this, believes that the consequences of a false positive treating a healthy patient are 1.5 times worse than those from a false negative not treating a diseased patient. So this shows that the clinician really wants models with as few false positive errors as possible. So for example, for the clinician ending up with 2 false positive patients, 2 patients who go through unnecessary treatment for coronary heart disease when they don't have it, that is the same or worse than ending up with 3 false negative patients. 3 false negative patients are 3 patients who have the disease but miss out on the treatment. So sending 2 patients for unnecessary treatment is the same or worse than missing out on treatment for 3 diseased patients. Because in this situation, 1.5 false negatives equals 1 false positive. And we can also visualize this here. I've added Squidward to the mix here. But now if we look at this probability threshold of 60%, as we just showed here, 3 false negatives is equal to 2 false positives. So here, based on this threshold of 60%, which is making it harder for you to predict positive, it's making it stricter. Not just the coin flip 50-50, but making it that you need a predicted probability of 60 or above to be predicted positive. You're being strict about being positive. Because 3 false negatives are equal or are equal to 2 false positives, or 2 false positives could even be worse than this. So here, wrongly predicting that 3 unhealthy patients, you see Patrick, Squidward and SpongeBob, they actually have very poor hearts. But wrongly predicting that these 3 unhealthy patients who actually have heart disease, are healthy. We're predicting that they're healthy. We see them celebrating with the cake and, pin the tail on the donkey kind of thing, or the hoisey. we predict they're healthy, they go out celebrating, but in reality, they actually have poor hearts and they're missing out on necessary treatment for coronary heart disease. So this type of mistake is is probably as equal to two false positives, or two false positives could even be worse than this mistake. And two false positives here are that we're wrongly predicting that two healthy patients have coronary heart disease and we're sending them for unnecessary treatment. So in this case, having these three patients miss out on necessary treatment for coronary heart disease is in a way equal to sending two patients for unnecessary treatment. But here, two patients for this mistake could be worse or the same as three patients for this mistake. So again, the emphasis is on minimizing false positives. And this is because our probability threshold is greater than 50%. Wow. If we have a probability threshold of 75%, we're making it even harder to predict positive. We're making it even harder for us to predict that a patient has the disease given the predicted probability. So again, we have a predicted probability from our machine learning model based on clinical features here. And our goal here then is to classify patients as having the disease, as being positive, or not having the disease, being negative. And here, at this very strict threshold of 75%, we are predicting that a patient is positive, that they have the disease, only if this patient's predicted probability of disease is greater than or equal to 75%, or 75% or above, then we're predicting positive for the patient based on their predicted probability. Otherwise, we're predicting negative, that the patient does not have the disease if the patient's predicted probability of disease is less than 75% here. So that's what this means. But if we had to quantify it, we would plug in the 75% in this formula here. So we would have probability threshold over 1 minus probability threshold, 75% over 1 minus 75% equals false positives over false negatives. And then we simplify this here. 75 over 25% is just equal to 3 over 1 equals false positives over false negatives. And then we just cross multiply, so we get 3 false negatives equals 1 false positive here. So 1 false positive is the same as 3 false negatives. So the clinician believes that the consequences of a false positive, of treating a healthy patient, sending this patient for unnecessary treatment, is 3 times worse than those of a false negative, of not treating a patient for disease. So this shows that the clinician really wants models with as few false positive errors as possible. And one of the reasons this could be is perhaps maybe in this situation, going for treatment, maybe could be very, very risky and very expensive as well. And there could be a lot of risks from going for this treatment than maybe missing the false negative, right? There could be many reasons for these. And these are all subjective and come down to your preferences. But again, in this situation, what this means is that ending up with 1 false positive patient is the same or worse than ending up with 3 false negative patients, because again, 1 false positive is equal to 3 false negatives here. For coronary heart disease, using the probability threshold of 75%, we said that 3 false negatives is equal to 1 false positive. So again, Squidward, SpongeBob, Patrick, they are celebrating thinking that they're healthy. These 3 poor patients actually have unhealthy hearts, and they're celebrating because we wrongly predicted that they are healthy. So they're celebrating thinking that they're healthy, when in reality, they need treatment urgently, and they're missing out on this treatment that they need. That, heart disease could spread to a very severe stage by the time they now detect it or something. So wrongly predicting that these 3 unhealthy patients are healthy, they're missing out on the treatment that they need. We are believing, based on this threshold, that this mistake is not as bad as 1 false positive, as wrongly predicting that 1 healthy patient has coronary heart disease and sending them for unnecessary treatment, when instead they have a healthy heart. So again, wrongly sending this one poor patient for heart disease treatment when they have a healthy heart, based on this probability threshold of 75%, we believe that such a mistake of sending this one patient who has a healthy heart for CHD treatment could even be worse than not sending 3 heart disease patients for heart disease treatment. That this mistake, wrongly predicting 3 unhealthy patients who truly have the disease are healthy, having them miss on treatment, given that their heart is in an unhealthy state, but we're thinking that they're healthy, that this mistake is equal, or maybe not as bad even, as one false positive as sending this poor patient who has a healthy heart for treatment. And maybe it could be the case that if a healthy patient has this treatment, it could be that maybe their life could be in huge danger or something, or maybe it could really reduce their life, and that harm may not be as bad as them missing out on this, because maybe at some point heart disease, whether you detect it early on doesn't make much of a difference. Who knows, but there could be many reasons for this threshold probability, but all that's saying is 3 false negatives are the same, or maybe even not as bad as 1 false positive, because we've made it so strict to predict positive, because we want to have as few false positives as possible, because false positive mistakes are worse than false negatives. So now if we keep raising the probability threshold, and so now it's 90%, that is very strict. That means that we're predicting that a patient is negative, even if they have a predicted probability of disease, up to like 89% or so. So basically, if the predicted probability of having the disease is less than 90%, we're predicting that patient is negative. Otherwise, we're predicting that patient is positive, that they have the disease. If the predicted probability of the disease is greater than or equal to our threshold probability of 90%. We're like, yep, you have the disease. 90% and above, predicted probability, you have the disease. That's what we're predicting. So based on that now, we're just going to plug in 90% as we've done before, guys. 90% over 1 minus 90% equals false positives over our false negatives. So that's just 90% over 10%. And that just simplifies to 9 over 1 equals false positives over false negatives, and then we can cross multiply here, just multiply these together. 9 false negatives equals 1 false positive. That's what this is here. So essentially 1 false positive equals 9 false negatives. So the clinician believes that the consequences of a false positive, of treating a healthy patient unnecessarily, are 9 times worse than those from a false negative, from not treating a diseased patient. So this shows that the clinician really wants models with as few false positive errors as possible, making it very difficult to predict positive. So if you end up with 1 false positive patient, the mistake is just the same or even worse than ending up with 9 false negative patients. 1 false positive equals 9 false negatives. To a doctor, preventing 1 patient who's healthy from going for unnecessary treatment is the same kind of a win as preventing 9 patients who have the disease from getting treatment. Since 1 false positive equals 9 false negatives, for the clinician, essentially preventing the patient who is healthy from going for unnecessary treatment, trying to prevent this false positive, it's that same kind of a win as ensuring that we prevent 9 false negatives, that instead we send 9 patients who are diseased for treatment. So preventing 1 healthy patient from getting unnecessary treatment is the same kind of a win as sending 9 diseased patients for treatment. That's what it kind of means in a way. And then now if we even raise it to 95%, it's kind of analogous. It's kind of like the opposite of the probability threshold of 5%, which is something that you'll see here. Because again, at 5%, it was, 1 false negative is 19 times worse than 1 false positive. But here it's going to be the opposite idea, because now we are predicting a patient is negative, even if they have 90%, even if they have 94%, as long as their predicted probability is less than 95%, we predict the patient is negative and does not have the disease. Otherwise, we predict the patient is positive and has a disease if the predicted probability that they have the disease is greater than or equal to 95%. So similarly, when we plug in this probability threshold into this formula and simplify it, 95% over 1 minus 95% simplifies down to 19 over 1. Cross multiplication leads to 19 false negatives equals 1 false positive. So instead of 9, which it was at the 90% threshold, it's even worse now that we can see. So 1 false positive equals 19 false negatives. So the clinician believes that the consequences of a false positive, of unnecessarily treating a healthy patient, this false positive, are 19 times worse than those of a false negative, not treating a diseased patient. So again, the clinician really wants models with as few false positive errors as possible. And if you remember, when we had this threshold at 5%, instead, it was kind of like flipped around. At 5%, it was actually the opposite, where 1 false negative was equal to 19 false positives. When ending up with 1 false positive patient is the same or even worse than ending up with 19 false negative patients. That's a lot, because 1 false positive equals 19 false negatives. So unnecessarily sending 1 patient who is healthy for treatment is the same or worse than preventing 19 patients with the disease from getting treatment for it. And again, this could be that maybe getting treatment may not improve your life as much as sending a patient for treatment who doesn't have it. Maybe there's so many complications, and maybe that's why the clinician really wants to be very sure about predicting someone's positive for the disease. And this could even be in COVID-19 situations. Hypothetically, maybe it's a resource allocation or something, right? You really want to be sure that somebody really has severe COVID before allocating those resources, because there's such a huge constraint on doctors, nurses, equipment, materials, ventilators. So you really want to make sure that they have very severe COVID before you send them for the treatment and take those spots away. But yeah, this is just how you can interpret many different probability thresholds here. So what you hopefully just saw from the example for the probability threshold of 95% and 5%, what I was telling you, is that the interpretation is kind of like the opposite. And the main idea I want to just show you through another example is that basically for a given probability threshold, the interpretation for 1 minus that probability threshold will just be the exact opposite. So hopefully this will save you guys some time. If we have a probability threshold of 80%, then the 1 minus 80% is just 20%. So again, guys, these two sum up to 1. 80% plus 20% is 1. So if 80% is a probability threshold, then if we also look at 1 minus this probability threshold of 80% as 20%, the interpretations will be exact opposite. So again, at the probability threshold of 80%, if a predicted probability for a patient is 80% or above, we predict positive. Otherwise, if the patient's predicted probability is less than 80%, we predict negative. That's what 80% probability threshold means. But 20% has an opposite, like instead it's kind of flipped around. And the area regions are the same though. But instead, if the patient's predicted probability of being positive is less than 20%, please predict negative. Instead of 80%, if it's 20%, then we predict negative. Otherwise, if the patient's predicted probability of having the disease is greater than or equal to 20%, we predict positive. Instead, in this situation, it was that if the patient's predicted probability of being positive is greater than or equal to 80%, predict positive. But here, it just has to be greater than or equal to 20% here. So based on other videos and what we talked about, since this probability threshold is, one second. Based on other videos as well, and what we talked about earlier, the idea is that, since this probability threshold is since this probability threshold is greater than 50%, and this one is less than 50% here, since this is greater than 50%, that means that false positives are worse mistakes than false negatives. And here in this situation, since this threshold is below 50%, it means that false negatives are worse than false positives. But just to motivate it, so if here the probability threshold is 80%, we plug 80% here into this formula. 80% over 1 minus 80% equals false positives over false negatives. That's just 80% over 20%, which we simplify to 4 to 1. We divide by 20 and then we get 4 over 1. And then we do something called cross multiplication again. 4 false negatives is equal to 1 false positive here. So basically 1 false positive is, the harm from this mistake is equal to the harm of 4 false negatives. That's what this means here. 1 false positive, the harm from that is equal to or even worse than the harm from 4 false negatives. So we really want to reduce false positives here. And that's also what we observe because this threshold is greater than 50%. Whereas if we use the exact opposite, 1 minus this probability threshold, if instead our probability threshold is 20%, where these two had sum up to 1, so we look at 20% now. So instead of 80%, we plug in 20% here in this formula here. 20% over 1 minus 20% equals false positives over false negatives. Then this ratio just becomes, instead of 4 over 1, it's just 1 over 4. And then similarly, we do this cross multiplication for false positives is equal to 1 false negative. So instead of 1 false positive, the harm being that of 4 false negatives, instead it's the opposite, where the harm from 1 false negative is kind of the same or even worse than the harm of 4 false positives. So it's a flipped interpretation, where here the 4 is on this side here, making a false positive 4 times worse than a false negative, whereas here the 4 just kind of changes, comes to the right, moves over to the side here, and instead 4 times worse is a false negative than a false positive. The way that we analyze a false negative and a false positive is kind of the opposite here, where one is 4 times worse than the other based on this threshold. It's just a matter of which one is 4 times worse than the other. And this number will change, as we've shown, based on the probability threshold that you use, but the interpretation will kind of be similar but opposite, for the probability threshold and its opposite, 1 minus that. And you can kind of get an idea based on this formula, because this formula is kind of centered around probability threshold over 1 minus probability threshold. So if we have the opposite on top, then it's just going to be a flipped interpretation. So the same would hold between probability thresholds of 10% and 90%, for instance, or 30% and 70%, or 40% and 60%. So the ideas are the same. What this ratio is just going to be flipped version of this. 4 here whereas 4 is here. The same equation, 4 here versus 4 here. And these two sum to 1. So I hope that makes more sense to you guys. So I just wanted to show some math motivation for that. So basically, probability threshold over 1 minus probability threshold equals false positives divided by false negatives, which is what we've been talking about. And that's kind of motivated by, decision curve analysis, which I talked about in other videos as well. So please do subscribe and see those. But the key idea, that we just saw for the 80% and 20% idea is that if we switch probability threshold to being 1 minus the probability threshold, so if we instead of having 5% as our threshold, if we look at 95%, then the opposite holds true. So essentially, what this becomes is 1 minus the probability threshold, if we plug in that for the numerator instead of probability threshold, and in our denominator, instead of probability threshold, we plug in 1 minus probability threshold, then the numerator is just 1 minus probability threshold, and our denominator is just 1 minus this, which just becomes 1 minus 1 plus probability threshold. The minus becomes a positive, and then that's just left with 1 minus probability threshold divided by, so these slash out here. So 1 minus probability threshold divided by probability threshold equals false positives divided by false negatives, which is kind of like the opposite. It's like the flipped over version of what this is. Probability threshold over 1 minus probability threshold equals this. Instead, it's kind of like flip over. It's like a flip around fraction. So now we have 1 minus probability threshold on top and probability threshold on the bottom. And the same thing on the right, it stays the same. So it's just that the interpretation is flipped. So basically for probability threshold and 1 minus the probability threshold, the impact is just the opposite. So let's see what that means. So just some examples here, like, 5% probability threshold and 95%, which is the opposite. 5% as a probability threshold, as we've seen, means that one false negative is equal to 19 false positives in terms of the impact of the errors. Whereas for 95%, it's flipped, where one false positive instead is equal to 19 false negatives in terms of the impact. And again, these two, 5 plus 95%, sum to 1. So for 10% and its opposite, 90%, instead we see for 10%, one false negative equals 9 false positives, whereas for 90%, it's flipped, where one false positive equals 9 false negatives. For 20%, one false negative, as we just saw right now in the previous example that we'd gone through, equals 4 false positives, and then the opposite 80% instead showed that one false positive equals 4 false negatives. So the same idea, but like instead of false positive on this side, this is a false negative equals 4 false positives, but instead one false positive equals 4 false negatives. Similarly, for 40%, one false negative is equal to 1.5 false positives, whereas for 60%, one false positive instead equals 1.5 false negatives. And then for 95%, so you saw the same thing here. So the same idea, except one false positive is equal to 19 false negatives. It's the same thing here, but this is just what I'm calling as probability threshold. And then 1 minus probability threshold is just this guy here, which is 5%, is one false negative equals 19 false positives. And we could keep going on, just listing the opposite. 2% for threshold, 98 for the opposite. What do those mean? Let's simplify those. And this is cute little Toggle. Hi, Toggle. How are you feeling, Toggle? Are you okay, Toggle? Are you okay, little guy? Are you angry? Toggle? Toggle? So just like cats are different, same are people's preferences. So we all have our own probability thresholds, our own preferences. So we're going to evaluate them here. Toggle? 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 Thank you guys for watching. Thank you. So guys, if this part confuses you, please do reach out to me with any and all questions that you have. I'm here to help. So please subscribe to my YouTube channel. Even Yangshi saying, please subscribe. Please subscribe. You agree? And please do see my other videos. I have a detailed video just going over the probability threshold of 25% and talking about it. And another video talking about false negative versus false positives for a probability threshold and talking more about the intuition here. But here I just wanted to talk to you about many examples of different probability thresholds and just to show you kind of again what those mean, to help cement the idea that probability thresholds are kind of like a currency, kind of like an exchange rate that they can give you some idea about how we weight these errors. And I want to quantify them for you to see what exactly they mean in terms of how many false negatives equals a false positive, or how many false positives equals a false negative, and vice versa. So thank you guys for watching. Mwah. So thank you so much for watching, and please reach out if you have any questions. And as my good friend Aina says,
Please like and subscribe.
yep, to my channel. So please do that and please share. Thank you guys.